Hi, welcome to the Byrne-Wheeler Report. My name is Joe Byrne with XPU.pub.
And I'm Bob Wheeler with Wheeler's Network.
So, Bob, there's been a lot of interesting news in the last few weeks. What's grabbed your attention?
Well, mostly I was covering hot interconnects and hot chips from August. August was a surprisingly busy month, and then also, Broadcom's had like three recent switch announcements, including Tomahawk Ultra, which is kind of the most surprising and different.
Right.
So, yeah, lots happening.
Yeah, I was there in person for Hot Chips, and I think you joined both conferences online, correct?
That's right. Yep.
Just to start the conversation from my side, and I covered this at xpu.pub, just a short item. Andy's network owns a company called Condor Computing in Austin, Texas, and they introduced a high performance RISC-V core. And what's interesting about it is really, under the hood, inside the technology, out of order CPUs have been handling instruction scheduling basically the same way since the 1960s when IBM pioneered out of order microprocessors. And the way Andes does it with Cuzco is they do the scheduling essentially in the front end of the CPU. They know all about the instructions that have preceded any given instruction, so they know when resources will be available, and they assign each instruction a specific time to execute. And then if there's, say, a cache miss that delays that time, they update it. So it should allow for a more power efficient and smaller design because you don't have a CAM or other type of circuit that's constantly checking for the next ready to run instruction. Because in theory, and apparently in practice, you can deduce when each instruction will be ready to run given the processing execution history up to that point. So I thought that was pretty interesting. The high-end RISC-V market is, I guess to put it politely, is still developing. There are a few options out there, but this is certainly one of the more interesting ones.
Yeah, so the Andes Cusco was pretty interesting. I guess the question is, what's the expected performance impact? And I guess the trade-off is you're saving some power, which could be applied elsewhere to get
Right,
equivalent performance, right?
right. I mean, I think the power is going to be on the marginal side, relatively small. Um, so probably most folks will just pocket it. As for the performance impact, they gave some numbers, but that was against the ideal. So I think against like an ordinary practical implementation of a comparable processor, it's going to be negligible, maybe 1 or 2% at most. But without the counterfactual, it's a little hard to tell. It's not like they created two processors that were identical, but for the scheduling approach.
Yeah.
So we'll see where it goes. It's RISC-V has created these opportunities for companies to innovate, and we'll see what the customer base thinks ultimately.
And then I think you were in Cambridge for ARM's Analyst Day.
That's right. ARM recently had an analyst day for their mobile client IP. So the CPUs and GPUs for smartphones, and every year they turn the crank and squeeze more performance out of their designs, or they introduce a new microarchitecture. First thing in here is the Cortex name is gone, and for smartphones and other mobile clients, they're using the Lumex name. And the other thing is, before for this segment, they had three tiers of CPUs. They had Cortex X at the high end, and then they had Cortex A700 series was the uh, big core, and then they had a little core in the Cortex A500 series. They've changed the names and they've added an intermediate tier. So it's for the first generation, they're all C1, so computing or CPU generation 1 under the new naming scheme. And the Ultra replaces the Cortex X. And what they're introducing this year is an extension of the microarchitecture that they implemented last year and the preceding year. And then there's the new tier, which is premium, which is essentially the Cortex X, but with fewer vector units and a smaller L2 cache, leading to a smaller silicon die footprint. And then Pro is the name for the 700 series replacement, and Nano is the 500 series replacement. And the Nano CPU is new this year, where they did some updates to, again, squeeze out more performance without impacting the area that much. I think it's in my article on XP.pub, but what I recall is something like a 5% performance gain for a 1% area gain. So net improvement overall. And I think we'll see the first smartphone chips be announced on, let's say, Monday, the 22nd of September, just to randomly pick a date. So a week from the day we're recording this,
Okay.
Implementing this IP. And then on the GPU side, it was kind of funny. They had introduced this premium name a few years ago called Immortalis. Well, the Immortalis name is dead. They're using the Mali name for both the highest end and the other tiers. But what they're doing is, again, they're using the same names as on the CPU, Ultra for the most advanced ones, and then I think it's Pro. I think they only use Pro for the lesser configurations. What's new here is they've updated the ray tracing, and again, the XP.pub article goes into details here, but there are different levels of ray tracing acceleration. So the first level is you trace that the ray hit a triangle, and then the next level you accelerate is traversing the data structure that tells you where the triangles are. So they've implemented that in this one. And I should say, I forgot to mention the big thing with the new Lumex is they've implemented SME2, which is ARM's second generation scalable matrix extensions. And keep it a little bit confusing, even though it's the second generation SME, these are the first ARM CPUs to implement SME. So we could talk more about that, but that's kind of a big deal, as it makes it easier for developers to do AI processing and other types of processing that use matrices. They can now accelerate that and get more performance inside the linear programming CPU-based model. So that's, from a technology perspective and a practical developer perspective, that's probably the big news is SME2.
Oh, okay. And what kind of vector cores are in the top-end Lumex core?
As with the Cortex X925 last year, they have 628-bit SIMD pipelines.
Okay.
And they implement SVE2 scalable vector extensions too, as well as I think the legacy Neon. And then I think the premium core only has 2 of those pipelines, but software is indifferent to the number of hardware pipelines. It's on microarchitectural detail, not an architectural detail.
Yep.
So what did you see that was interesting at Hot Chips?
Well, so on the RISC-V vein, it was interesting that Nvidia kind of revealed more about their ConnectX 8, so-called
Yeah, I
Super
saw
NIC.
that.
And now, you have a better idea of why it's called a Super NIC when you kind of see the insides. And it turns out some of this isn't really new, but it's sort of the first time they've unveiled some of the internal architecture. And so one of the interesting things was that ConnectX 8 actually has a 16-core RISC-V processor, which they call the
Right.
event processor. And it turns out that this block was already there in ConnectX 7, but you wouldn't have really known about it unless you went searching developer docs. And so, kind of the previous Super NIC was Bluefield, right, which had an ARM complex. And
Right.
now they're able to implement the functions that they need for SpectrumX just using this 16-core RISC-V event processor, so they don't need the separate ARM processor. So it's both, more efficient, but also kind of removes the need to have these two different types of NICs depending on what protocol you're implementing.
Right. Yeah. For a while, NVIDIA's roadmap is they had Bluefield on it for a while, but there was no successor to it, and it's like it's not dead yet. But it was, they were kind of hinting that they were going in this direction.
Yeah, so one of the interesting comments from the speaker was that the ConnectX 8 is like the south bridge of the GPU.
Right.
And the reason is because it has this integrated PCI Express switch. And then it also has what they're calling a Spectrum X Ethernet switch integrated. I don't think it's actually a switch. It's more like an 8-port MAC. But the point being that you have 8 by 100 gig ports coming out on the network side, so that you can do spraying and all of the kinds of things you need to do for load balancing across
Right.
a rail optimized topology. And so they're kind of showing that it's much more than just a basic NIC. It's got the PCIe switch on the kind of the host side of the world, and then the network switch or multi-port MAC, whatever you really want to call it, on the network side of the world.
Right. So it's kind of like a fabric adapter toward the switch, right? But
Yep.
it's very much it's far more sophisticated than that, being able to handle a lot of advanced NIC functions.
Yeah, so that was
I do think. Oh, go ahead, please.
yeah. So I mean that was pretty interesting, although not a new product, but some kind of new disclosures in terms of the internal architecture.
And I do think when we consider RISC-V versus ARM, at the high end, one area where I do think ARM is vulnerable is designs like this, where the software stack is quite limited, that needs to be run is quite limited. The number of people in the world who actually program it is quite limited. So I think it's an area where Neoverse, which is ARM's brand for infrastructure CPUs, is vulnerable. It's in these more deeply embedded designs with limited demands on the software ecosystem.
Yeah, basically factory firmware. It's not expected to be customer programmable. And that is a difference from Bluefield, right? With Bluefield, the ARM cores were customer programmable, and so it's a little bit of a different animal.
You don't think that a major data center customer wouldn't opt to program this?
Well, it's certainly possible. The question would be how broadly NVIDIA would want to open up the tool set, I guess. But yeah, that's certainly possible.
I mean, my experience with customers, they often say they want to do something, but it's more like they don't want to be told no. And once they kind of hear that they can, they ask for it. But customers don't have the time or the wherewithal to monkey around with things.
Yeah, so the other talks in that networking session at Hot Chips were the other NIC talks were the AMD and Intel talks, and AMD talked about their Pensando Pollara 400 NIC, which is a 400 gig NIC.
Now for AI.
Yeah, but what's not really clear is how Pollara differs from Selena, which is their standard 400 gig NIC. They both use P4 pipelines, and the only obvious difference from kind of an external standpoint is that Pollara doesn't seem to have external DRAM, and so they've probably stripped off the DRAM interfaces. But other than that, I think the P4 pipeline is probably identical between Selena and Pollara. Somebody actually asked, and there wasn't really an answer
Yeah,
that made any sense. So
there wasn't really a good answer. But why would they not need DRAM? Do they not need the buffer to reorder packets on ingress?
I think they don't need a, that large of a buffer is the issue. So
Okay.
they're able to make do with on-chip SRAM, it seems.
Right. And then Intel talked about Mount Morgan, their next IPU, and it also has a CPU array in it, right?
Correct. Yeah, the IPU, which we would call a DPU, has the ARM array, which is the same as the first generation. The interesting thing on Mount Morgan is that Google actually did a keynote at Hot Interconnects and talked about the fact that they're implementing their Falcon transport protocol in hardware, and that's actually Mount Morgan that has that Falcon transport block built in. And so, whereas AMD has this P4 programmable pipeline, the Intel design seems to be more kind of hard coded for the Falcon transport protocol, which means that it won't be able to support UEC. At least the current silicon apparently does not support
Right.
UEC, whereas AMD is claiming that Pollara will support UEC.
Yeah, and that could be something if they had to make any substantive changes to Pollara, I would assume it would be that they would have, if there were any blockers keeping them from implementing UEC, they would have addressed those.
Yeah, absolutely.
Uh,
So yeah, and Intel said they have Mount Morgan in the lab, so it's basically kind of at a sample stage at Google. It sounds like.
right, with Google being their main customer, and um, do they have any other like huge customers, or maybe just some smaller?
No, I don't think. I mean, it took them so long to make it generally available, the first
Right.
generation, that is, that I don't think they have any other major customers for it.
And also these DPUs have they go on to network adapters at the data centers like Google. I'm sure if Intel had something comparable on the AI processing side, it could be maybe adapted for that. And then the Pensando stuff's gone into some network switches and appliances too, right?
Correct. Yeah, there are some smart switch designs using and appliance designs both using the DPU. So it's something we've seen at Microsoft and elsewhere. I think there's an HPE smart switch as well. So that is a way to kind of add intelligence to what would otherwise be just an Ethernet switch, or to build a high performance appliance where it's not just the CPU doing all the heavy lifting.
Right. Because that's a very flexible design on the data path side of the P4 engine, which the Nvidia has a P4 engine too, ConnectX, right?
It's not
So
a P4 engine.
that's
They
not
have a
P4.
multi-threaded processor that's in the pipe in the
Okay.
data path, but
Right.
they have not made it P4 programmable. P4 has very specific kind of match action constructs, and it doesn't necessarily map that well to different architectures. So I think there's sort of a narrow P4 camp, and then there's everybody else.
Hmm. Right.
Well, I think the other recent news was, Tomahawk Ultra from Broadcom, which is really was pretty surprising because it wasn't really on Broadcom's roadmap. It wasn't something that we expected. And all of a sudden, there's this whole
Right.
new switch architecture. And it really is a new architecture, even though they used the Tomahawk
Tomahawk.
branding.
Right.
It's not Tomahawk. It's a new pipeline design. It's a new memory architecture. It is really an entirely new architecture because it had to be to get the kind of latency that they're claiming on this design, which is 250 nanosecond port to port latency, which is
I mean, they did things like they moved fields within the Ethernet header, presumably to get them at the front of the packet. I'm assuming, is that correct? So they could start cutting through early, like nanoseconds earlier.
yeah. I mean, they do have a proprietary header format, but that's not really required to get there.
Okay.
And so, the more important thing is they basically created a design that can do 64 byte packet streams, and much higher packet rate than Tomahawk. So they needed more pipelines. They increased the clock speed on the pipelines. But of course, the die size is about the same as Tomahawk 5. So the trade-off is, smaller packet buffers. So it doesn't have as much SRAM because they had to free up space for the pipelines. So
But at the same time, they for these AI applications, they're not going to use. They don't need the SRAM, right?
correct, yeah. So they don't need the deeper buffers for AI, and so that's the trade-off. But I mean, from an external standpoint, it's pin compatible with Tomahawk 5. So it's 512 by 100 gig SerDes, drops right in. It's the exact same SerDes design. So it's a 5 nanometer design, and so it's essentially a drop-in replacement, which means that customers can even build systems around Tomahawk 5 and then drop in Tomahawk Ultra when it's qualified for production. So
Yeah, that's great for market adoption. Kind of takes out the barrier that has to be crossed to deploy systems
yeah, I mean, at least on the physical layer side, and then
on the physical system.
from a performance standpoint, the other important thing is link level retry, which cuts down on the performance impact of any sort of packet errors by doing the retry in hardware, and then credit-based flow control is another big add. So both of those are optional features in the UEC spec. So those are not proprietary.
I did ask the architect if the switch could actually run regular Ethernet because it is, the protocol as described and the behaviors are a little bit different. And he's like, oh yeah, if you send it any kind of Ethernet packet, it can switch it. But I think realistically, it's probably realistically, Windows only just switch UA Ethernet.
Yeah, yeah. Realistically, it's a scale-up switch, and it's not going to be used where you would normally use Tomahawk. It's definitely not a Tomahawk 5 replacement. So I think Nvidia CPX,
Yes.
another surprise announcement.
Yeah, that was kind of out of the blue that there is. I mean, they communicated before their roadmap rather publicly with that after the current Blackwell, there's Blackwell Ultra, and then there'll be Rubin, and then Rubin Ultra, and then this is slotting time-wise between the two Rubins, but it's addressing a slightly different problem set.
Yeah, and at first I was really kind of scratching my head as to why they would sort of disrupt the the homogeneous architecture of the NVL72, right?
Right.
And then once you start looking at the details, you realize, okay, it's a single die design. It's using GDDR7, so it doesn't require CoWoS. It's going to be, quite a bit cheaper to build than a Rubin, right? So,
Right. I
significant.
think also they may, uh, they're they're pretty much selling everything they can make, and they may be co-op and possibly alternatively HBM constrained in production. So, if they can move, or if they can at least not make that a risk factor and fulfill some of their demand for processing in the abstract to this other chip, it benefits them as well as it benefits their customers who maybe were effectively deploying full fat Rubin chips, not for the processing, but to get more memory. That's a pretty expensive way to get memory capacity.
Yeah, and I mean, and conceptually, it kind of looks more like the RTX Pro than the full-blown, Blackwell, right?
Right. It's monolithic and it has video encoding and decoding. What else are you thinking of?
and no NVLink.
And no NVIDIA.
Yeah. So,
Oh, that's interesting. So, if for them to move the KV cache from Rubin to Rubin CPX, they're going to have to do that over PCI.
yep, PCIe.
Interesting.
Yeah. I mean, the other interesting point was that they're sort of dropping four of these into the compute tray, and I would think they'd be kind of pushing the upper limits on power on the Oberon rack. So, they made it sound like it's a drop-in, but I don't see how it can be from a power perspective.
Well, I guess it depends on how much they populate the rack, right? Maybe it's half full.
Yeah, so I mean, there's got to be some um, power and thermal increase when you drop four additional processors into the compute tray.
Right. Yeah, it'd be nice if they had some diagrams. There's some marketing pictures where they just sort of photoshopped in some chips. But it'd be really nice to be able to understand the system design. And especially when we think about that there has to be GDR as well. It's going to take up some board footprint. I was thinking the alternative is Samba Nova is a data center NPU company, and what they've done is they have a lot of on-chip SRAM, and they have HBM, and they have external DDR. So, that gives their customers the option, like, hey, we have a big memory footprint, they can spill into DDR. I think still, to the extent NVIDIA is actually matching processing to memory capacity for a given stage of processing, so they're talking about the token generation stage in LLM here. I think this more bespoke approach makes sense. But yeah, it'll be interesting to see how different this is from an actual RTX chip.
Yeah, I mean, I think the compute performance is going to be considerably higher than RTX, but I
Right.
don't think we know exactly what the numbers are just yet. So,
Yeah, and most companies are kind of resource constrained, and but NVIDIA is not short of resources, and they're not short of demand. So I'm willing to bet the business case for this was probably not hard to pencil out, especially if it alleviates, capacity constraints as well.
yeah, but it definitely complicates the messaging and kind of the now you've got racks that are more purpose built for specific types of workloads. So it definitely complicates the message on what customers should be deploying depending on what their workload is.
Right. On the other hand, customers plural. At the end of the day, there are very few huge customers, and maybe this doesn't address the long tail but rather addresses the short tail of folks who are buying GPUs in million unit orders.
Yep. Oh, we were talking about NVLink Fusion. So,
Yeah, NVLink Fusion, which is NVIDIA's name for enabling NVLink to work with non-NVIDIA processors.
correct. So there's really two flavors. There's the flavor that's for custom CPU integration for, let's say, a hyperscaler with a custom ARM processor. And for them, it's NVLink C2C, intellectual property integration, and that's a forwarded clock kind of wide interface, something that you
So
can
easy to do the silicon integration and validation of
relatively easier to do the silicon integration if, with just
relatively.
IP. Yep.
Right.
And so, I don't think they've disclosed the details on the latest C2C implementation, but the last sort of disclosed version was 40 gig per lane, 40 gigabits per lane, and is clearly a forwarded clock, single-ended signals, that kind of thing. So
Right.
pretty straightforward chip-to-chip interface. Not clear exactly how far they can drive across the PCB, but I think you pointed out that there's pretty good span between Grace and Blackwell, right? So
Yeah, I mean they're on a board together, so they're on the same board, but they're not touching.
yeah,
Like,
despite
and
NVIDIA's super chip terminology,
right. I mean, it certainly is a super chip.
it's really not a super chip.
Right.
And
It's a
then,
module.
yeah, so the other flavor, which is perhaps more puzzling, is the custom
Yeah.
XPU side of it, where they're going to allow a customer with their own in-house XPU to integrate NVLink 5 and connect into that NVLink 5 backplane like in an NVL72 rack. And in that case, the path to integration is an NVIDIA supplied chiplet. So the chiplet implements the NVLink SerDes so that they have sort of a, guaranteed interoperable SerDes implementation. And it's UCIe on the chip-to-chip side. So customers just have to integrate UCIe in their ASIC.
Right.
And so the big question there is who wants it, right? And who's actually
Now,
going
who
to
wants
use
it,
it.
and why would NVIDIA indulge them? I mean, those are kind of like two questions. Who wants this, and
Yeah.
why is NVIDIA going along with it?
Um,
Yeah, we'll see. Maybe somebody has something like their own chip optimized for recommendations or something fairly, you know, maybe not obscure but specialized, and they think it's better than using another NVIDIA GPU. I am not sure. It's definitely puzzling who would want it.
but presumably NVIDIA wouldn't go through the effort of creating a chiplet if they didn't have demand there, unless it's simply in the name of openness and trying to portray themselves as more open, in the face of UA link and competitive pressures.
Yeah. Personally, I would be a little surprised if they really care about that. But yeah, I mean, another couple possibilities are one is they really don't think this customer's design is really going to pan out or pose a big threat to their business. Like either it'll have technical failure or it'll be a small piece or something like that. And so they took some NREs from them to implement this, and ultimately they just don't see it as a big threat. That's a possibility. What do you think of that?
Well, I mean, they do control the licensing terms, right? So it's,
Right.
they open is a relative thing, right? And they can decide who they want to provide the chiplet to. And so, yes, they could limit it such that it's for kind of bespoke workloads where it doesn't directly compete with a kind of more general purpose GPU.
Right. I mean, it's also possible this was, there was some kind of competitive threat where it just kept people inside the Nvidia camp. Where it was, if you don't do this, we're going elsewhere, is what a customer said.
Yep.
Maybe. Another possibility is it could be, say, like a national lab or a defense organization has, it's a kind of a variation on what we talked about. They have some proprietary price processing that they need to do, but and they're building this huge scale design, and then they just decided to open this up.
That's an interesting thought. There could be that's an interesting angle. It's definitely possible.
Right, but I think it'll be a while before we know.
Yep.
We've been kind of hush-hush about the details. It's been good talking to you, Bob.
Thanks, Joe.
And I'll say to the audience, if you enjoyed this discussion and you think others would benefit from listening to it, please tell 4 friends. And if you want more information about either of our analysis, on my side, you can go to xpu.pub, and on Bob's side, go to wheelersnetwork.com. And until next time, be well.
It's all about the Pentiums, baby.